Let's go through another example of calculating R3 and L3 for this integral here. It's a slightly different function from the one we had in the previous slides. It's x cubed minus 7x from 0 to 3 dx. So R3 is going to be, well, we have this interval 0 to 3. If we cut it into 3 equal pieces, each piece is going to be of width 1. Our right endpoints will be 1, 2, and 3. So it'll be f of 1 plus f of 2 plus f of 3 times delta x. In other words, more specifically, it'll be 1 cubed minus 7 times 1 plus 2 cubed minus 7 times 2 plus 3 cubed minus 7 times 3, all multiplied by the delta x, which is 1. Work that out, come back. If my calculations are right, you should get negative 7. What about the left endpoint, the L3? I'm going to remind myself that I got negative 7 for R3. Okay, so L3 would be f of 0 plus f of 1 plus f of 2, all multiplied by delta x, which is still 1. So we have 0 cubed minus 7 times 0 plus 1 cubed minus 7 times 1 plus 2 cubed minus 7 times 2. Again, all multiplied by the delta x, which is just 1 here. Work that out, come back. You should get negative 12 if my calculations are correct. So R3 is negative 7, L3 is negative 12. So now the question is, why were we getting negative estimates for our answer? Well, it's very similar to the previous function we looked at. If we graph this function, we're going to get a tiny sliver of positive area here above the x-axis and a large bunch of negative area. So we have with definite integrals the notion of signed area. When I say signed area, I mean signed area, like area that has a sign on it, positive, negative. And it just has to do with whether it's above or below the x-axis. Here's the midpoint rule we started to talk about in section 4.1. We talked about it kind of informally, but this is the notation we use. It's delta x times the sum of the function values of when we have the midpoint of each subinterval plugged into the function to get the heights of those rectangles. Delta x is b minus a over n, and xi bar, that midpoint, is given by this formula. It's the average of xi minus 1 and xi, which is the midpoint of that subinterval. So then how would we use this to calculate an estimation of the integral from 1 to 2 of 1 over x dx? Again, it's just an approximation. And we're approximating with 5 rectangles this time. So we have our interval from 1 to 2. What does it look like if we break this up into 5 equal pieces? Well, what is each of these going to be? The length of our interval is 1, 2 minus 1, and then we're cutting it into 5 equal pieces. So each piece is going to be 1/5 or 0.2. So this is going to be 1.2, 1.4, 1.6, and 1.8. Now what are the midpoints going to be? The midpoints of each interval, the midpoint between 1 and 1.2 is 1.1. Midpoint between 1.2 and 1.4 is 1.3, and so on. So those light green numbers are the midpoints that we're going to plug into the function. And what's our function? It's 1 over x. So what we have now is that m5 is going to be the sum of 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5. This is me evaluating the function at each of these midpoints of the subintervals multiplied by my delta x, which we said was 0.2. Work that out, come back. I got 0.691907886. Hopefully you got something similar.